yeah, so this meeting is being recorded, and if you don't want to be recorded, just don't say anything. But feel free to ask questions. That's an important part. Hi, again, I'm Sue Coppersmith. I'm a professor at the University of New South Wales in Sydney, Australia. And on behalf of the Aspen Center for Physics, I'd like to welcome you to this lecture. And this is a free physics lecture sponsored by the Lukin Foundation. And this foundation has supported these lectures for 30 years, for 30 ventures. In their generosity, the generosity of the foundation and the generosity of every lecturer makes it possible to bring these lectures to you. Oh, and also, I forgot to thank Emily and all the staff who are just wonderful. And, you know, we're very excited that you get to see the center and see some of the work that is going on. And these lectures are a way that the center can thank the Aspen community for its wonderful support over the years. This week, the conference that we're holding has the title Quantum Simulation with Quantum Hardware, and it is about the latest advances in quantum computing and in quantum simulation. And during the week, we have some formal talks and discussions, but we also have the opportunity to meet on the ski lifts, on the cross-country trails, and on the snowshoes. And it's really a wonderful environment, and we're really very excited and grateful to be here. As Emily said, the schedule is on the back of your program, and there's a series of lectures. And if you want to be on the mailing list, you can sign up. You can either go onto the website, but also there's a sign-up sheet outside the website. So today, now I want to introduce today's speaker. He is Professor Mikhail Lukin, who is currently the George Vasmer Leverett Professor of Physics and a co-director of the Harvard-MIT Center for Ultra-Cold Atoms and of the Harvard Quantum Initiative in Science and Engineering. There's a longer bio in the program, but I just did a few so that you know that he's a very eminent guy. He's an author of over 100 technical papers and has received many awards, more of which are listed in the program. I just wrote down the Niebuhr Bush Faculty Fellowship, the Willis Lamb Awards for Laser Science and Optics, and the Norman Ramsey Prize. And he's a member of many honorary societies, including the National Academy of Sciences. And he's done a lot of groundbreaking research in the field of quantum computing and quantum simulation, some of which he will tell you about tonight. The subject is New Frontiers in Quantum Computing.
Thank you very much for the great introduction. It's a great honor and privilege to be here. So I don't know if many of you are aware, but this Aspen Center of Physics really plays a very special role in a worldwide physics community and basically advancing frontiers of basic research and our knowledge, understanding of the universe. And we're really grateful both to those who work here, who support the center, but also for a broader Aspen public whose basically support and generosity will rely upon. I will talk today about the subject of quantum computing. And this is something that you probably have heard about. In fact, it's nowadays very hard to avoid hearing about that. And some of this kind of news and headlines, depending on your point of view, either exciting or maybe alarming. So, and there is a lot going on. So there are some companies which both big and small, which invest in this field. Some of them become public. And there are these ideas of quantum cities being proposed. So what I'd like to do is to try to answer a little bit about what is it all about, where we are going, and what can you expect from this. The foundation for that is that information, its acquisition, storage, and transmission and processing are fundamentally related to physics. Because this is being implemented, carried, encoded in some physical objects. And the progress in technology over the last several decades clearly points to the fact that the ultimate elements of sensors, processors, and transmitters will be quantum size. A simple way to visualize it is by virtue of something which is called Moore's law, which can be expressed in several different ways. One way to think about the size scale of the transistors, or in other words, the number of atoms per bit stored. And what you see is that, early on, like in 60s, 70s, 80s and 90s, there was basically a very rapid scaling down, reducing the size of the transistor, which came also with increase of memory of the devices, increase of the speed. But then, if you kind of extrapolate this curve, what you see is that this kind of moment arrives where basically this number of atoms per bit becomes on the order of 1. At this point, the behavior of particles and objects can no longer be understood in terms of classical mechanics, like Newton's law. And for a while, people were very worried about what's going to happen, when this moment will arrive. So it actually turns out that engineers are very ingenious. There are many ways to extend this Moore's law. There is no mistake. Sometime the time comes when we really have to kind of enter with the computing and communication and measurement devices the realm of quantum mechanics. And while for a while it was considered as a kind of as a worry, as a limitation, then people already a couple of decades ago realized that this single atoms, single electrons, single nuclei, and single photons, which are basically fundamental constituents of the matter, they can be used to acquire, carry, store, and process information. And but the problem is we cannot really think about them as a classical objects. We have to think about them quantum mechanics. And quantum mechanics has been a branch of physics which has been basically developed around 100 years ago, and has been tested and explored in many experiments. And despite of that, all of us, even those of us working in this field, are still often surprised about the properties that quantum mechanical systems can have. One of the most striking properties is something which is called quantum superposition. Basically, what is quantum superposition is, this is like a statement that in quantum world, objects can be in multiple places at once. It's kind of like illustrated by this, trajectory here that basically it's here, very appropriate here, and the mountains. And moreover, this kind of idea of superpositions, they can be also extended to objects which are non-local, which can be basically separated by kind of long distances. That's the idea of quantum entanglement. So basically, this kind of quantum entangled objects based in the superposition state, display this kind of very, very counterintuitive, very unusual correlations. Now, it is all sounds very odd, but through the century of experimentation, we know that at the microscopic world, physics really is governed by the laws of quantum mechanics. If you don't believe me, so maybe you can believe a Nobel committee. So there's basically over 100 years, worth of Nobel prizes, started with Einstein and Niels Bohr, and culminating with last year's Nobel Prize, which is actually given precisely for this kind of studying these concepts of quantum entanglement, this kind of very unusual counterintuitive correlations. If we take these concepts and try to kind of apply them to the ideas of information processing, computing, we end up with the idea of quantum computer, the main topic of my lecture today. So basically, what is quantum computer? Quantum computer is a device which is capable of processing information in a fundamentally different way from classical computers that has never existed today. And so in quantum computer, bits of information are replaced by something which is called quantum bits. And these quantum bits can use effects, can exploit effects such as superposition and entanglement, which I just talked about. So when used correctly, this kind of system can potentially solve some problems much, much faster than the classical computer could ever do. So let me try to kind of elaborate on that a little bit. So basically, in every modern computing device, almost in every computing device, the information is presented as a string of zeros and ones. So, and basically, through this of zeros and ones, by kind of making addition, multiplications on the strings, that's how we basically, do everything now, related to basically electronics, communication, computing, and things like this. And quantum computer basically replaces classical bit of information by something which is called quantum bit, which is very similar to this classical bit. It can also be, the system can also be in a state 0 and 1. It can also be in a superposition. It can be at the state 0 and 1 at the same time. That's this kind of superposition. That's kind of, it's a very small change, but actually this change can have a really profound property. So consider, for example, a string of single atoms, and I will tell you in a second that this is actually no longer a thought experiment, but consider it as a thought experiment, a string of atoms. And in each of these atoms, let's try to encode bit 0 and 1. And now, if it's a quantum mechanical system, we can also think about superpositions. In particular, what one can now do, one could build superpositions of these different combinations of zeros or ones. And there are many of such combinations, there are exponentially many. And that really has a profound property. So in particular, if you use this kind of idea of superposition, and if you have a relatively small computer involving 300 quantum bits, remember this number, this kind of small and simple object, in principle, simultaneously store and evaluate more solutions than number of particles in the entire universe. And that's why that's why people are excited about it, about this direction. This is what's called exponential speed up. And the idea here, again, is that you place this register superposition of different states. And, the quantum computer, if used correctly, can, can basically evaluate information stored in this entire superposition simultaneously. That's this idea of quantum parallelism. So, how can these kind of, unusual devices change the world? I will tell you right away that we really do not know the answer, and it will be a theme of my talk. But, we have some ideas. We have some ideas where to look. And potentially, they could be useful to solve difficult problems which are currently being solved, with very expensive brute force method, which lead to suboptimal solutions, or potentially, possibly, they can be solved some problems which are completely impossible to solve with any classical device. To make these kind of things more specific, so the kinds of things that people are thinking about, one is understanding and designing new quantum materials. I will talk a little bit about it. Also trying to model and understand chemical structure and processes, this area, but potentially related to fields like drug design. The other class of the problem involves optimization problems, and they are relevant for networks, for logistics, for many of the things which go around the world. But this class of kind of impossible problems, one of them involves fitting big numbers and number theory, and it's very much related to encryption. So it's actually something, again, which is, sounds kind of esoteric, but this is something which we rely on in everyday life. And there are also thoughts that potentially quantum systems can, speed up already kind of these amazing things like, artificial intelligence and things. But again, the important thing, this field is in a very beginning, at a very nascent stage, and you probably do not know the most interesting algorithms and applications of quantum device. So depending on which problem you want to solve, you often would have to use different type of quantum devices, and sometimes we call them programmable quantum simulators. I will explain what it really means. Or sometimes we like to think about universal quantum computer. Universal quantum computer means that it can do, this device can do anything which an arbitrary system, quantum system can. Okay, so these are all kind of theoretical ideas, but the question I would like to address and kind of elaborate upon is whether we can build these quantum machines in practice. And to answer this question, I'll go back to one of the pioneers in this field of quantum computing, Richard Feynman, someone who actually, I'm sure, spent a lot of time here in Aspen. And kind of about 40 years ago, he started, wondering, about whether it would be ever possible to build the computing, systems, which transistors, which will really have a size of one atom. And he said, oh, such a nonsense is very entertaining for professors like me, and I hope you will find it interesting and entertaining as well. So I also hope that you will find it interesting. But what happened in the last 40 years, there has been a lot of progress actually to build these machines. In fact, there is now a wide variety of platforms where scientists were able to isolate a small number of these quantum bits and manipulate them. And there is a big scientific community which actually pursuing this kind of idea. That's part of this excitement why what that I indicated, I alluded to in the beginning of my talk. But at this point, you could say, okay, so if people were able to build this, transistors which can control single qubits, so why can't they build a big, quantum machine? So it actually turns out that even if you start with this kind of isolated qubits, putting them together to make a useful machine is actually challenging. In order to illustrate this challenge, I would like to use this kind of, concept which I sometimes called ultimate quantum rivalry. So I kind of maybe by now it's a little bit loaded kind of statement. You can think about different ways. So you could think about competition between different of these platforms as a race towards build, useful quantum computers, or maybe competition between different countries. But actually it turns out it's none of them. It's actually much more, it's a competition between different forces of nature. One of these forces is what I would call controllability. It's basically the ability to isolate and control individual quantum objects, and keep these objects quantum mechanical. And another is scalability, because to really build useful quantum machine, we need a lot of these objects. We need them to work together in a way which keeps the system quantum mechanical. The reason why the latter is challenging is because in our world around us, the objects like the stable, for example, which in principle originally built from quantum particles, but clearly you can touch it and it's that is just it does not display any of this kind of weird concepts which is shown here. The reason is that as the object becomes more larger and more complex, they kind of lose their quantum character. So, and that's a challenge. You have to start with these systems involving individual quantum particles, and put them together in a way that really preserves their quantum character. And kind of the key is control. So, by the way, in case this was too complicated, so this controllability and scalability is a common, problem, the sort of the tension between them. So, for example, like I like to think that, if you, for example, have like a big organization involving, for example, a lot of PhD physicists, and bring them into, one room. So by definition, such an organization will be very difficult to control. So, and this is manifested, but this is manifested here kind of as a real kind of scientific and technological change. Okay, so in truth, right now, we do not know if truly large-scale machines, involving millions of, very good qubits which do not have errors can ever be built, and how. That said, this field is now at a very exciting juncture, and I like to call this kind of current state of the art is the era of quantum discovery. So basically, we're at this point, which I hope to illustrate, where we can actually build systems which are large enough, quantum enough, programmable enough that we can control, for example, systems involving over 100 quantum bits. And such systems already do things which you cannot model using any classical system. And basically, as such, they become kind of useful tools, scientific tools, to explore, for example, scientific applications, to start testing, classical algorithms. And most importantly, these experiments which we carry now, the knowledge which we gain, helps us to build bigger and better quantum machines. In what follows, I'd like to illustrate it with, one example of research direction, in particular that my lab is involved. And this kind of idea actually goes back to Richard Feynman. So in his early musings about quantum computers, he started thinking about making computing device in which numbers are represented by a row of atoms, with each atom in either of the two states, 0 and 1, and that's our input. And then the Hamiltonian is basically, it's kind of is a technical jargon, indicating that quantum dynamics, you allow system to kind of proceed with quantum dynamical evolution. And then ones move around, zeros move around, and finally a particular bunch of atoms is being measured and represents the answer. And he basically says nothing could be made smaller, nothing could be made elegant. So this actually kind of became like a prediction or more like a prophecy. It actually turns out to be really true in our laboratories and experiments which we are doing. So specifically what I'd like to do, I'd like to focus now on building quantum machines literally from individual atoms using light as a control tool. And the key idea here is that dielectric objects such as atom can be suspended using a laser beam due to light pressure. So it turns out that if, for example, I take the laser pointer and shine it on the wall, basically these photons in my laser pointer push wall just a little bit. So this is the idea of light pressure. And it turns out that you can actually use this kind of forces, light forces, to basically grab and hold on to a single atom. So that's this kind of idea of optical tweezers. To illustrate this, I will actually show the movie. And this movie is made by one of the pioneers in this field, by Ted Hench. Another pioneer is Arthur Ashkin, who's actually received the Nobel Prize for optical tweezer invention, has been actually a frequent visitor here to Aspen. In fact, I learned that his brother, Julius, has been one of the founders of this center. Okay, but the movie is from Ted Hench. And so what is shown in this movie is a pattern of some kind of light beams. It's actually a pattern created by technique similar to the one which is used to project these lights on the screen. And so it's a kind of a hologram, which actually, if you change it in time, a little bit, so this hologram starts to move. You can also make a much more fancy hologram. So, for example, his hologram here, this has this kind of little spots, laser spots. So, and what will happen in the movie now, this kind of light patterns will be put on this kind of tiny polystyrene beads, which are flowing in some liquid. If you look at carefully, you see that now by moving these light patterns, these beads start to move also. It will be actually, so here, for example, you can really see that this, like these beads kind of start a line to form almost like some kind of artificial crystal. And so that's the idea. So the year is 1994. So this is actually Ted Hench. I think he was at the time at Stanford, who started making this kind of thinking about this idea. So actually, it turns out that these systems, these ideas can be really used to build artificial crystals, single atoms. And these single atoms can be literally held by the focused light beam. Here is an approach to building quantum machine, literally atom by atom. In this approach, what we do, we shine a large number of these focused light beams into the vacuum chamber, to the basically vacuum tube. And in this vacuum tube, there is a small pressure of atomic gas. And so basically, each of these focused light beams then can capture a single atom. And what you see here is that, usually this capture is not kind of very homogeneous. So for example, some traps can capture the atom and some are not. But what you can do to basically remove this disorder, you can literally take a picture of atoms and figure out which traps are full and which are empty, and then basically eliminate the empty trap and then rearrange the rest in the desired configuration. So this is the starting point. That's how we built a kind of quantum register. And then to make a computation, what we do, we use lasers to actually excite these atoms into a different state. We basically use lasers to effectively change the atom size. And that way, the atoms can kind of interact, and that's how we can do things like logic operations and things like this. And this actually a joint project in collaboration between my group, my colleagues at Harvard, Marcus Greiner, and colleague at MIT, Vladan Vuletic. I must say this project, already ongoing for almost like a decade, and it's really a lot of fun. So let me just, kind of do a little bit of physics, Yeah. So basically, how do we make the atoms talk to each other? What we do is we actually shine laser light, of a certain color to try to basically change its state from this kind of this natural state of the atom, where the atom has a small size, to the state where the atom has much, much larger size. And it's clear that if it increases in size, the atoms will start talking to each other. So basically, what happens is that you can increase the interactions by many orders of magnitude. Essentially, what happens here is that the kind of when the atom is large, the basically electronic orbits kind of get modified a little bit. So that's this kind of interaction. That's this mechanism. I should say here that the technique that we use to do this atomic size change in a very controlled way, something which has been invented by another famous Stanford physicist, and actually he is present today in the audience. It's Professor Steve Harris and friend, so it's great to see you guys. So we literally use the techniques which Steve developed, something like 50 years ago. Okay, so, and these are, okay, I should say that these ideas, have been also proposed originally by Ignacio Chirac and Peter Zoller, two famous theoretical physicists who also spend a lot of time here in Aspen. There is another Aspen connection. I have many of them. Basically, to make kind of a long story short, the way how we will run our quantum device will be actually like this. So we'll first start by preparing single atoms in a register. So basically, these are now pictures of single atoms. You are looking at single atoms, let me emphasize. So what we do, we basically assemble these single atoms in some kind of groups, like registers, and shine laser lights, pulses on them to kind of change their state. Then finally, we read out the state of the atom. That's our answer. That's really implementing this Feynman's mission. And the quantum logic we do by exciting the atoms into these Rydberg states, using laser light, using basically techniques that Steve developed. I should say there that there is actually a big effort in the community. And in fact, two of the pioneers in this effort, Dave Weiss and Mark Safman, actually also here at the conference. Dave is sitting. I saw him coming in, yeah. But this kind of this field now at a very, very special point, as I hope I will illustrate. This, just to show you kind of state of the art. So we are basically, making now arrays, of 300 or so atoms. We start them by trapping around 600 atoms in this kind of disordered configurations. And then what we do by moving the atoms around, we prepare, for example, arrays like this. We prepare this desired configurations. And the rest we keep as a kind of reservoir. We can still use these atoms if we want. So then, of course, what we do, we excite these atoms in Rydberg states. That's how we do this quantum logic and quantum operation. So what I'd like to show now is not quite a real-time operation of this experiment. It's a little bit slowed, I think, because it's projected over Zoom. But this is more or less what we see in the kind of how basically single atoms now are trapped and then positioned and arranged in the way how it's kind of designed. So the state of the art, as I already mentioned, we can operate systems of about 300 atoms, and we can place them in kind of any desired configuration if you want. This is an artificial two-dimensional crystals. And if we want, we can sometimes, position them at random, at will. So, for example, in program arrangement like this, I press a button, and here is the arrangement is realized. I should say, using this tool, it's really kind of a very special time in our lab, because we can really explore a lot of different directions. And this is something that we enjoyed in last years. I will give you some little bit of indications. A lot of that is really involving, studying physics of complex systems, but there is some work that we are doing which is actually going towards solving real-world problems. And last but not least, the machine of the type which I described is now publicly available. You can actually log in and play with that, and it's actually available through our startup company, Quora Computing. It's actually across the Charles River in Boston. Well, let me go back now to this. Actually, before I proceed, I should say that the research direction, the part of the broader effort in the community. So, for example, one other direction involves essentially taking this kind of atoms, which I described, and literally ripping electron away, so to make the underlying atom, like a charged particle. It's called ions. Actually, this ion trap quantum computers is actually something that has also been a field which has been pursued for almost 25 years by now. So, in fact, trapped ions and superconducting qubits are perhaps two of the most mature technologies, and hear a lot of them. So basically, with ions, you can also arrange them in the form of strings, and you can use the ion motion because they repel each other to kind of do this so-called quantum logic. And basically, shining lasers, you can also manipulate the atoms. So a lot of similarities to the approach which I described, but there are also differences. And in fact, the trapped ions have kind of really implemented some, state-of-the-art experiments where researchers can control tens of ions. And actually, this is also one of these machines which is now kind of available. You can kind of log in and play with that, for example, through the company called Hank. Okay, so let me kind of go back to this question, if and how quantum computers can change the world. The first thing I'd like to discuss is, this kind of idea how we could use programmable quantum machines to understand and design new quantum materials. These quantum materials are fundamentally quantum objects. That's why it's very hard to kind of describe them classically. It's a very natural fit for these quantum machines. And so basically, one kind of advance along these lines that I would like to highlight involves realizing the 50-year-old goal, kind of long elusive goal in the field of material science related to something which is called topological quantum materials. This idea has been kind of invented by a famous physicist, Phil Anderson, who basically postulated that there could exist some very special form of matter, the unusual form of matter, which cannot be described like a, gas, liquid, or a crystal, and he called it a quantum spin liquid. I learned just before my lecture, Phil was here 22 times, visited Aspen 22 times. I'm sure some of these ideas, have been developed by talking to fellow physicists and this, walking around between Aspens. But then I've heard the story that when he came, he was at Bell Labs at the time, he came to Bell Labs and he gave a talk about that. And he was by that time, very accomplished, scientist, had a Nobel Prize. And I actually talked to some people who were present at this talk. And basically, apparently after this talk, people came and talked to him, said, oh, you are amazing, you're great, but this stuff, don't talk about this. And in fact, his first paper was published in some kind of obscure conference proceeding, But basically, what happened was that, and kind of his idea was essentially that is like the state of matter is encoded in something which is called systems topology. Systems topology is basically the concept in geometry, which helps you to classify objects by their shapes. So from the point of view of topology, for example, a donut is identical to the coffee cup. The reason is that there is this kind of hole, is one hole in the donut which translates into this hole, this coffee mug. Basically, what it really means is that you can continuously deform the donut into this kind of coffee mug without breaking it. So basically, if you want instead a donut hole, you would really need to cut this thing and basically, shrink it into this, And actually, what happened was that despite the fact that this idea was kind of very, very abstract, very obscure, over the last 50 years, many of the in the condensed matter physics community really picked it up and kind of realized that it could be potentially very, very powerful platform because these properties of materials kind of relate to the fact that to the topology, which basically remain intact under twist deformation, but not cutting. And basically, as a result, these topological states could be very, very robust. In fact, one way to build quantum computers is to use states like this, to use this topologically protected state. In fact, if you think this is very kind of abstract, hard to understand, let me just tell that this kind of idea of topological bits is the basis for the entire quantum program in Microsoft Corporation. So basically, and so essentially what they're trying to do is they're trying to use it as an ingredient kind of build quantum computers. There is one problem. Problem is that despite 4 decades of kind of exploration, up to now, there has not been really a conclusive experimental evidence that such states can exist in nature, in any real world systems. But this is like, let me pause it here, a little bit, slow down, and think about it. So basically, these kind of ideas are so intriguing that Microsoft basically invests in kind of building quantum computers based on system which may or may not exist in nature. So that's why, one could use now quantum machines to try to model and to understand when such states can be created. And in fact, about 2 years ago, using this atom array platform, we were able to actually, for the first time, implement realized state like this. So this state is actually very odd. So it's basically a superposition. It's this kind of, again, idea of superposition of the atom array in many different kind of, states at once. So this is why it's quantum. That's why it's intriguing, and basically now we can kind of create such state. We can kind of poke and probe with that. So this is actually a picture which was created by the Scientific American artist, maybe 2006, many years ago. I'm sure that this artist, kind of decided that this physicist went completely crazy, because, stuff like that, it's basically what this picture represents is making excitations in this spin liquid and trying to move them around. They're kind of some very weird things happen, but actually in our experiment, we can literally implement these things where these excitations are created by laser beams, which can be moved around and create and probe this excitation. So basically, using this kind of system, we can really gain unprecedented insights into topological matter. Now, this provides us with a tool which is complementary, in some way more powerful than our analytical theories or numerical simulations. And there are many exciting applications. One of them is simulating nuclear physics problems, which actually is something that we're already doing. It also gives us insights to designing practical topological materials, in particular using atomically thin materials. And actually, I would like to mention that about a month, there will be a public lecture about that by Pablo Herrero. So he's actually an MIT physicist who is actually one of the pioneers in these two-dimensional fields. And I strongly encourage you to attend it. Last but not least, as already indicated, so realizing, states and ideas like this, can really be a starting point to explore this kind of new ways to do information processing, which which is much more controllable, which are robust to errors. So this is actually really exciting, and this is again one example. There are many other approaches. So for example, there is another way to build this quantum model using something which is called optical lattices, which is basically creates this kind of periodic potentials for atoms, and when the atoms can move around, can tunnel, and actually this line of research also allows you to gain insights into models for high temperature superconductivity, where so far there is a lot of kind of mechanisms and physics which are not very well understood, and kind of this basically allows you to look to models of quantum materials with kind of unprecedented degree of control, where you can basically look and follow kind of one atom at a time. So in short, these tools, at least in terms of their scientific applications, they are already paying off. Basically, this is what this conference is about. In this conference, what we are doing, we're talking about ideas, for kind of building new models of these quantum simulators, and thinking about what to do with them. To kind of give you a little bit of historical perspective, I'm thinking often the quantum computers are now somewhere, where classical computers were in kind of early 1950s. So this is a picture of one of these, classical machines. So clearly you needed a screwdriver and maybe soldering iron operated. So this is the case with quantum computers right now. But already at the time, these machines, they were useful to carry out kind of scientific experiments, scientific simulations. And this is where we are now. So in fact, we can take the systems and put them into corners of universe, if you want, and no one has ever been. If you do it in the right way, in a controlled way, you always make discovery. This is very, very special. So, but I want to also talk a little bit about other things. So scientific applications is not the only thing why people are excited about quantum computers. So in fact, to kind of prepare this public lecture, I thought about how to kind of introduce all of this kind of more real world, if you want, applications. And I decided, kind of, I must say, advised by my students, to use modern technology. So in fact, what you can do, you can just ask GPT about what are the applications of quantum computers. So, and it's actually not bad, So some of the key applications, include drug discovery and material science. Material science is something that I talked about. It's actually true. Cryptography, breaking commonly used encryption models, methods is also true. I will talk a little bit about that. It's challenging in practice, but that may be possible someday. So, okay, machine learning, I think here it shows clear bias. GPT wants to improve itself, so and the last thing, okay, this should be understandable. So the supply chain optimization, improving logistics, reducing waste, and increasing efficiency, that it's good. It can be bad, In fact, this is related to kind of potential application of quantum computers to solve hard classical computation problems. So they actually, turns out they have many practical applications. The problems, they're actually kind of abstract mathematical, so they're typically formulated in the form of graph. Let's consider, for example, a graph like this. So it's basically a graph has some nodes, vertices. They're connected by links, so it's like a network. So it's similar what you see in the back cover of your airline magazine, when you sort of fly. So this specific problem is actually it's called maximum independent set. So here, basically, what you want to do, you want to color as many of these nodes as possible, but you cannot color the two nodes which are connected. That's what's called maximum independent set. And the question is, can quantum computers, help us solve this problem? I should say that this ChatGPT is quite impressive. It's going. Says these are some of main areas where quantum computers have the potential to make an impact. However, much research is needed to fully realize potential. So and it's actually true. So just to kind of emphasize this point, so this kind of optimization, graph optimization and sampling, this is kind of a little bit more technical, are indeed, problems which are related to many areas kind of everyday activity, traffic optimization, placing antennas, when things like epidemiology. Right? So basically, when do you kind of need to, encourage people to get revaccinated, in which areas? And so these are often related as network problems. So question is, can quantum machine accelerate the solution of this problem? So let me give the honest answer. In truth, we do not know. But, it's an exciting possibility. And we as a community are working to find it out. And in fact, these early quantum machines are already super useful to kind of try to answer this question. So here is one example. It's actually quite recent work, again, from where we basically take one of these combinatorial optimization problem and actually encoded it into this kind of atom array. Basically, each node now is single atom, and the connectivity is determined by the range at which these atoms interact. And basically what we do is shine laser pulses to try to kind of, excite as many nodes as possible, but subject to this constraint that two connected nodes not be excited. And using this approach, supported by DARPA in collaboration with Query Computing, our startup company, what we did is basically we just created hundreds of graphs and through it basically try to train our machine to solve them. And actually this type of work, it's way too detailed here, and I'm sorry for showing it, but it's kind of shows you the scale. So we can now operate with systems of about maybe 300 qubits. This means that the graphs which have 300 of these nodes. And actually, in some cases, we really see that quantum machines can outperform kind of conventional classical solvers. There are two conclusions which one can make from this kind of thing. So first off, it's actually very exciting that, quantum machines can actually use for acceleration. But of course, we would like to now scale this up. And instead of 300, nodes, go to systems with tens of thousands of nodes, which that would make this kind of things practical. So the question now is how to scale up this kind of programmable quantum machines. That's the last thing that I will talk about. And this is actually related to kind of solving this these types of problems. So to really solve these problems, we need machines which are universal and which really operate without errors. So one example of the work along these lines is illustrated here. So up to now, what I told you is basically the way how our machine operates is we position atoms at will, and then we turn on this quantum evolution. And then we read out the result. Well, actually, you do not have to work in this way. What you can do instead, you can, position atoms, turn on quantum evolution, create some, connections between qubits, and then basically stop this evolution and move atoms around and start this evolution again and move atoms around. So in a way, this kind of what it means is that your computer chip essentially becomes like a living organism. So it changes, it reconfigures in time, the evolution proceeds. So this is actually quite unusual. I weren't in quantum or in classical kind of architecture. And what we did, for example, using the system, we built this kind of topological error correcting code. So we use this topology to improve robustness. I don't really have time to describe it, but basically the idea here is to use redundancy, is to use a lot of single qubits, physical qubits to encode one logical qubit. Then what you do, basically do a majority vote. If one of the physical qubits changes state, you do a majority vote. Then, if more of them are still up, still in state 1, it's probably 1. So this, connected with topology, really enables you to really protect the information. But this making this kind of thing on a torus seems kind of hard. We have two-dimensional system. How do you do it? So actually, in order to do it, use the idea which comes from the times when you still have magnetic memory, your hard drive. Remember, there were spinning disks, where you would you'd be reading, So at the time, is people like Ignacio Chirac and Peter Zoller proposed the idea that maybe you can exchange this magnetic memory with just a single particle, quantum particle qubit, and it could be like a quantum magnetic head, which would move around. So we actually implemented this idea. Instead of one qubit, we moved the entire array. So we moved the array of 8 qubits, which now goes, and these red dots indicate quantum operations between them, and basically, and we move them away and basically kind of, read them out. So that's the way how we created this kind of code on a torus. In fact, if you want to read about it, this actually, kind of very exciting because it allows us to kind of think about path towards large-scale fault-tolerant quantum algorithms. And if you want to read about it, it's actually, yesterday was an article in Nature, popular article of explaining this thing. So I want to kind of wrap up, but I want to just take maybe 2 minutes to connect where I started. So I started by saying that there is like an industry around it. So you could ask even what I'm telling you, what is this industry about? So in fact, I myself is involved in a startup company called Quera Computing, which basically builds machines of the time which I've described. And the big event of 2022 was that one of these machines, became publicly accessible through the AWS cloud. So this was kind of one of these, hello world moments, So it actually has, 256 qubits, you can program it. And in fact, this is, something which actually, basically now everyone can do. And so kind of the idea is that you just, code, you program, where atoms should be kind of sitting, the geometry, kind of determine the connectivity, define the pulse, and then basically, run your experiments and kind of analyze your results. And this all is in a machine which has actually over 100 qubits. It really is kind of heralds kind of this new era of kind of quantum discovery. And so this is actually quite exciting, and we are looking forward to new collaborators and team members. In sum, quantum computing and quantum science and engineering is a new, exciting interdisciplinary field which combines basic science, device engineering, applications, and eventual products. We are entering this era of quantum discovery where we can use quantum machines for scientific applications, and also perhaps we are on the cusp of some quantum industry where new potential real-world applications products can be foreseen. I'd like to conclude this lecture noting that thinking about the future is a dangerous thing. So this is a picture of the first transistor. Now, who could imagine that, this would, some years later, result in this kind of, cloud computers run by single chips or even by the computer in your pocket. This was completely impossible to predict. So likewise, I think it is impossible to predict, where quantum computers will make an impact. But this is now an exciting field. It's an exciting field of science, and it's starting to become an exciting field of technology. So with that, I'd like to thank you for your attention and also leave you with, some stuff. We also sometimes have fun. Thank you very much.
Do you want to draw questions or do you want me to? All right, questions. I see a question.
I have a question. Can you imagine a quantum telescope and could it be used to explore dark matter?
It's a very good question. So the question is, can these ideas of quantum computers be used to build better telescopes? And if so, what type of things they can enable? So as a matter of fact, this is a research direction, and it's something that even my group is involved a little bit. So, and the most direct application of that is to kind of building a very long baseline optical telescopes, which are basically connected through like realistic lossy fibers. It turns out that if you cannot, if this fiber is too long, then there is loss in the system. And what you can do, you can use kind of ideas like this to do something which is called quantum teleportation. You can use non-local correlations, entanglement, to transmit, for example, information obtained, received with one telescope, to another. I mean, this is very challenging to do in practice, but potentially, for example, it could allow to really extend the telescopes kind of into completely new domains which are previously kind of accessible. And potentially one application could be to look at kind of dark matter in new regimes. Some of this research is actually both ground-based, and people are also thinking about satellite networks. Some of that is actually very exciting and very much ongoing. It's technically very challenging. Most of the things in this field.
So when you're talking about your like your computer, that
exactly.
new one, or even these lattice works that you're making with the laser lights, at what temperature is all this occurring? Is this at room temperature or?
That's an excellent question. So these are, thank you. So these are, if you want, vacuum tubes. So these are basically atoms suspended in a vacuum. So the system itself is at room temperature. However, atoms which are in the vacuum being slowed down, if you want, effectively cooled, this is done by laser light. Use laser light, decelerate the atoms, and really bring them at a still. That they can stay there. They can stay there for minutes at a time. And so basically, if you want, it's sort of a best of both worlds. On one hand, it gives us completely isolated, system where the atoms don't move, but at the same time, the system is actually at a room temperature. There's actually there are a lot of benefits to that. So some other approaches, for example, superconducting qubits, they require cooling systems, to very low temperatures. This kind of the methods to slow and cool atoms is again something that in our community, the techniques which have been developed by early laser pioneers like Steve, and others.
Okay, any other questions? Oh, I see a question.
So when you were talking about the registers, is that complicated in the CPU?
Yes, it is very much compatible. So this is indeed very much analogous to the CPU. For this moreover, for this kind of more advanced architecture, for example, an architecture where you can sort of move atoms around, you can in fact think about kind of like CPU, memory, and the RAM, kind of analogous. And in fact, there is some work like done by actually leading, computer architects trying to figure out how to sort of optimize and make these things work together. But it's actually a very exciting direction also at the interface of physics and computers.
Okay, I think we're out of time, but I want to thank everyone for coming, and of course, thank Professor Lukin for, really exciting talk. And there won't be a quiz, but you can always YouTube, it will be posted. But anyway, thank you.
Thank you so much.